Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly.
Hello everyone and welcome to the webinar. My name is Kevin Gaunt and I shall be the moderator for this webinar. The webinar is entitled How Fish-Friendly Pumps Have Improved Land Drainage Pumping Station TOTEX and will be presented by Martin van Nieuwenhuyzen from Aquatic Control Engineering. There will be a short time for questions and answers at the end of the presentation. But please note the presenters' details, which will be shown during the Q&A session, should you wish to contact them for further information. Please post your questions using the Q&A button in Microsoft Teams. Details of the next webinars will be shown at the end of this session. So thank you, and I would now like to hand over to Martin, if you're there, Martin.
Yes, I'm here.
Okay,
thank you, Kevin.
Over to you.
Let me just share my screen. Hopefully you can see that, Kevin.
Just bear with me a second. Yeah, that looks fine. Thank you.
Very good. Yeah, hello. I'm Martin van Nieuwenhuyzen from Aquatic Control Engineering. And today I'm talking about the fish-friendly pumping technology. I'd like to start off by exploring what the two available options for fish-friendly pumps are. On the left, you've got a more conventional axial flow type pump, and on the right you've got an Archimedean screw, but with a difference, and that's of course very fish friendly difference. Why do we need to consider fish friendly pumping? We've never considered it in the past. Land drainage pumps have been built since the early 1900s and even before. The problem is in the past, nobody looked at the consequence to the environment. What were we sacrificing in order to pump the water out to sea and create all the arable lands and protect our properties? Well, we're damaging a lot of fish, of course. A lot of the pumps inside pumping stations, the fish pass through the pump and are damaged, as you can see by the image on the right, which shows varying degree of damage, which happens to an eel. And the image on the left also shows an option that is being used quite heavily in drinking water applications or water abstractions, which is fine screening, but it's not fit for purpose for land drainage pumping stations. The reason is fine screenings tends to be at 90 degrees to a watercourse, so the bulk of the water is passing past the fine screens, and of course you're only abstracting from them. For drinking water or irrigation, for example. But at a land drainage pumping station, the pumping station is the end of the line. So the entire water body has to pass through the pumps or the sluices on the pumping station, which means the flows are much larger, the amount of debris you're going to catch is much larger, and you can suffer problems such as impingement, as you can see on the screen on the left, with the three fish which are almost effectively glued to the screen. So land drainage pumping station, we need to do something other than fine screening. Why do the traditional pumps kill fish? Well, nobody designed them for fish. We always looked at quality, speed, how fast can we get the pump to go? And the reason the speed is important, because the higher the speed is, typically the smaller your pump can be, and that of course drives down cost. The problem with the smaller and the faster pumps is that we get even more fish kill. You can imagine with an impeller, if you're going much beyond 500, 600 RPM, yeah, dependent on the pump size, even with the best hydraulic design, you're still going to be damaging fish. And all of this is to suppress cost. However, does it on a TOTEX point of view? Because a small pump going very, very fast lasts, of course, a lot less long than a large pump that's sort of just gently ticking over. And then what about the fish? Well, that just wasn't being considered. So what happens if you put the fish first, rather than the capital expense or capital cost of a pumping station? Well, this experiment happened, and it started with the screw pumps. Traditionally, screw pumps damage fish as well, less so than a standard axial flow pump, but they do. Now, it was really an experimentation to create the perfect screw pump that wouldn't damage fish, which is the starting point of all modern fish-friendly screw pumps. To really think about how to design a pump for fish, we've got to actually go back a step and say, well, what kills the fish in the first place? With screw pumps, it's blade strike, which happens from the middle or the lower red arrow on your screen. And that's because there's a leading edge which strikes perpendicular to the water, also perpendicular to any passing fish, of course, which is why they get damaged. And then there's the pinch point, so an area between the screw and trough, which has always got some space where fish can swim between, get trapped, pinched, caught. And to illustrate this, you've got the image on the left-hand side of an eel which was caught in an Archimedean screw turbine and suffered a broken spine. You can see from typical open trough screw pumps that mortality rates, which are shown on the right-hand side, these are three typical monitoring reports. Anywhere between 42 and 14% mortality is suffered. So you make a fish-friendly pump by removing those things that kill the fish. So we've got an Archimedean screw pump, which was designed specifically to be fish-friendly. So you've got a tapered leading edge. So this is a completely swept profile that glides into the water, and it means that there's no risk of the fish being caught by that perpendicular leading edge. The whole drum rotates, so rather than a static screw in a stationary trough, the entire barrel spins, and therefore you remove the pinch point. There is nowhere for the fish to get caught. And you can see that with this arrow here, that is completely laminated shut, so there's no gaps or anywhere for the fish to get caught. And what that produces is a very smooth operation of pump with low damage. The pumps are also able to operate even slower than open screws are, and that's because there's no run back to compensate for. Every drop that enters the pump travels up the screw and comes out of the end, while with an open trough screw, that gap which kills fish also allows water to permeate back down the screw, and therefore you lose quite a bit of efficiency, but it means you have to keep the tempo of the screw going in order to get the water up before it slides back down. So this is at Bells and Mockets, and each one of these pumps has a flow rate of 1.75 cubic meters per second at only a speed of 22 RPM, which is quite phenomenal. Now, we design these pumps specifically for fish, but there's also a huge economic argument to them as well, when you look at the thing from a TOTEX perspective, rather than just a capital perspective. First of all, you can see from installation here, you can lift the entire screw pump, motor, gearbox, frame in a single lift. A traditional open screw, you need to position the bearings and the motors and everything separate, so the installation time costs a lot longer. And also your civil works tend to be more bespoke, while here we're able to cast pretty simple concrete structures to allow you to place the screw. Now this screw was tested by a Fike net. This isn't the net at the actual pumping station, but we don't have a photo from the monitoring report, unfortunately. But it's essentially a series of nets that come into each other and trap eels, much as like a wasp trap catches wasps in the same kind of fashion. They're heavily tested. So you can see here, nearly 1,000 fish passed through, 934 to be exact. The nets are lifted at various intervals, roughly once every week or two, and the fish are examined and checked for damage. You can see out of the 934 fish, there was one which was damaged, but when you read the report, it was expected to be caused by the net rather than the pump itself. The other thing which is crucial here is the length of the fish. I'll show you on some other examples, but quite a few companies like to stick to fish which are under 15 centimeters long. The reason for that is, of course, below 15 centimeters, they've got the highest chance to get past that leading edge of a screw. Unfortunately, our rivers aren't that selective, and we've got fish all sorts of sizes. So we need to be testing it with fish of all sorts of sizes. This was exactly the fish that was in the watercourse. We didn't introduce any fish from other places, so it gave a true reflection on what was actually there. The other part where the screw pump is improved by its fish friendliness, specifically for TOTEX, is that we're able to reduce the overall lift of a pump for many applications. The red arrow indicates where the tipping point or the bottom of the screw typically needs to be for a Archimedean screw. The reason for that is if the pump is shown in a situation as you've got in front of you, the water can slip between the screw and the trough and constantly pass downstream when the pump is stationary or rotating backwards, in which case it's a hydroturbine. What we do is apply a brake to the motor so we can hold the shaft completely stationary and we can stop the pump rotating backwards. Therefore, the pump in effect becomes a line of defense. We still recommend the secondary line of defense. It's always good practice on flood defenses to have two lines of defense. But what this means is that you're able to actually put the screw and install it below the maximum outfall level. So if your maximum outfall level is up here, the screw can be installed down here. Now, to put this into perspective, what the difference that makes, I can show you this project that we did on the Isle of Sheppey. So Isle of Sheppey is on the Thames estuary in the lower Medway in Kent, and we installed here two 2.5 meter diameter Archimedean screw pumps, the fish friendly type, as you can see here. These weren't lifted with the frame because the dynamics of the site meant that basically that crane had to do the job, and it couldn't lift the pump and the frame as one, but we could lift it in separate parts. Now, when we take the next photo, you can see here where the pumping station building is. All of that is that level because the screws are essentially in a situation where they would pump against the head of water at a maximal highest tide event. If we did it with a traditional Archimedean screw, this pumping station would be 1.5 meters higher on the outfall than it is here. That's 1.5 meters extra height. That's more concrete, more steel piling, a larger building. The whole structure becomes much bigger with a lot of concrete, which is one of the worst materials we have in terms of carbon footprint. So it's a much more environmental solution. We're not pumping that extra 1.5 meters up at low tide or when the outfall level is low, which of course is reducing the amount of energy you're consuming dramatically, and overall more efficiency, less energy, smaller building costs. Yeah, you've guessed it, the best TOTEX solution you can find. One thing to remember for fish-friendly pumps is always to use HDPE non-return valves. The reason for that is cast iron is heavy, as is stainless steel. It doesn't open as easily as this, and essentially it's all well and good having a fish-friendly pump, but if you're shooting it straight at a heavy cast iron non-return valve, it's not going to do the fish much good. This is a nice video to show you again how you can see how the asset is sat in the flood bank rather than the pumps pumping over the flood bank. So this concrete level here, with a traditional screw, would have had to be level with the top here. The whole asset would have been much bigger, and that's where the fish-friendly pumping technologies really come into its own. It's a nice project, this. ACE delivered not only the screws, but we also did a full mechanical electrical package, including the kiosks and the non-return valves, stop logs, etc. So, looking at axial flow pumps. Well, you can see why the journey began with the Archimedean screw, because the axial flow was a natural progression from there. You can see the shape of the hydraulic, where the stainless steel design, the axial flow design comes from. And this was, how we started to look at how to make a fish-friendly axial flow solution. The reason it's fish-friendly is because, again, that swept leading edge has less chance for any kind of impact. It's not as likely to strike any passing object as a blade which was 90 degrees perpendicular to anything coming through it. To show this, you can see the blue typical axial flow kind of impeller with a 90-degree leading edge at the top and the fish-friendly design at the bottom. On the left, you'll see a chart, and the blue line shows the chance of impact with a fish of approximately 20 centimeters with the blue design as well as the pink. And you can see that it's much less likely to come into contact with the impeller with the 25-degree fish-friendly design than the traditional axial flow design. Now, fish-friendly pumps have to be variable speed pumps. So again, the fish friendliness is driving the industry to adopt more and more speed control. Traditionally, that wasn't used very much on land drainage pumping stations. A lot of the starters were just delta starters, which would just be running pumps at fixed speeds. Now, the variable speed drives kind of pay for themselves in themselves. The reason is because they use so much less power to operate your land drainage pumping station. So this example shows a flow curve with a fixed speed. So this is one impeller speed. Along the bottom, you've got the flow rate, and up the side, you've got the head difference. Now you can see that as you work towards the end of the curve, your pump is working far less efficiently. You also, at the end of the curve, you start to see issues potentially happening, vortexing, drawing aid in, possibly cavitation if you're really pushing it. Whereas if you're reducing the pump speed as the head difference reduces, you're pumping at a much more efficient rate and also lower kilowatts. So you can see direct comparison of kilowatts. You've got far less when you slow the pumps down. Now there is of course an argument, well, you slowed the pumps down so you're pumping less. Do you not win maximum efficiency there? Well, not really. When you look at the relative reduction, so that's the reduction per cubic meter per hour, that flow rate you're passing, rather than the direct reduction, you can see at the second point we're 14% more efficient, and at the bottom point, we're 38% more efficient. So again, a lot of power that's saved. And fish friendliness is driving this a lot on a lot of the land drainage pumping stations at the moment. It also helps with the fish friendliness. As I say, why do we need to slow the pumps down to make sure they're fish friendly? Well, this is why. The faint red lines that are being shown are rough fish mortality. On fish-friendly pumps, it's not that at a speed, it's totally fish-friendly, and then you go 2 RPM higher and suddenly everything is being killed. It's a gradual process. So the faster the pump goes, the more fish you're going to be damaging. So this gives an example, bottom line about 270 RPM, the dotted one at the top 423. And you can see that you go from 0.5% of the fish being killed all the way, yeah, these lines are very compressed down here, but maybe 15-20% of the fish are being killed. So you can see when you work towards the back of your curve, if you're working on a fixed speed of 423, then yeah, your fish mortality is going from 3% to 5%. If you can slow the pump down, you're keeping the mortality much lower. 1, 2 and 3% rather than 3, 4 and 5 as you see here, particularly because you're staying away from the back end of your curve, which is where a lot of the fish damage is caused. See here, reduction of about 80%. So the variable speed aspect is not just good for fish, it's also good for your TOTEX, it's using less and consuming less energy, and it's keeping your pump away from the parts of the curve where you'd rather your pump not go to ensure maximum longevity. Now, with the fish friendliness, how do we know it's fish friendly? How can we really demonstrate that? Well, of course, we first did a lot of research into the pumps directly to see, where are the lines, how is it working, all sorts of things we've done with ballistic fish. But then it's very important that you also do in situ tests, and we've done loads. In Holland, a lot of the pumping stations that were delivered, it was a requirement to do a fish-friendly test on, and all of these tests show absolutely outstanding results. We've noticed that there's a reasonable drive towards trying to create a fixed standard of what is fish friendly, and really dictating with that standard, if you have these parameters, it's fish friendly, and if you have those, then it's not. And unfortunately, it's not as black and white as that. We can say that we do meet with the new NEN fish friendly standards, but that on itself does not guarantee a fish friendly solution. You need to really understand what creates the fish friendly pumps and the parameters that you're working within. And you can only do that when you're the original designer of the impeller and you've developed the whole system from scratch and a starting point. To give some more case studies, to give you an idea of how we've improved the TOTEX on various assets. This is down near Romney Marsh in the southeast, Kent. And believe it or not, the pumps until not that long ago were still being operated with a heavy oil engine, single cylinder. Beautiful as it is, and it is now in a museum, it's not what we should be using in the in the 2020s anymore. So this was all removed. This image isn't the actual motor, because that was removed before ACE actually started the contract on this pumping station, but it is a replica of what was there. We removed the old pumps. There were some challenges. It was an extremely shallow sump because the pump was an end suction pump in the past. Therefore, it would be primed with a vacuum, and then you would pump the water. But that doesn't need a very deep sump. And the big challenge was actually to find a pumping solution that would work in a sump with only such low impeller submergence. So we were able to work with the customer. We do the CFD in-house. Having the ability to do that CFD as the pump supplier is also huge added value, because it means that you can really know where the edge of the pump is and where the edges of the capability lies. Installed new pumps and control panel on this particular project, as well as non-return valves on the outfall. What the outcomes was no more diesel being consumed now, much cleaner electric pumps, proven fish friendliness, less heat, improved flow dynamics, huge amounts of efficiency gain as much as 30%. So it's not just an environmental benefit, but again, huge TOTEX benefit as well. Talking about flap valves, as I said, we need to be looking at using lightweight materials, HDPE, for example, that moves completely out of the way, enabling a large open area for fish to pass through. But again, there's less head loss on these valves than there is on the old cast iron ones. So again, you're improving your TOTEX. There's also less maintenance to be carried out. You don't need to lubricate the hinges, for example. It's all self-lubricating, and therefore less maintenance. Generally, yeah, again, lower TOTEX costs. This is a live project that we're delivering at the moment at Keedby Pumping Station, which is one of the largest land drainage pumping stations in the UK. The situation they had here was actually that they were also end suction pumps. So using a vacuum to create and prime the pump lines before starting up the impeller. That was not a very robust system. Vacuum systems are notoriously unreliable. So by going with an actual flow pump, we were again able to create a solution which was much more robust, much more efficient than the previous pumps, which were all again driven by big diesel generators. We're now working with electricity, which is a much cleaner fuel or energy, particularly going forwards as we get more wind power, solar power, and that kind of thing. So
Martin, we're in the last 5 minutes, just to let you know.
Okay, that's great. Yeah. So again, improving, reducing the total life costs because we're not using fuel, we're using a cheaper energy. We've improved the whole layout of the pumping station, making it much more maintainable. Yeah, and got rid of a dirty fuel source, as well as making the whole station fish friendly. One really exciting development with our kind of pump technology is that we might be able to start looking truly at making carbon neutral pumping stations. This is a horizontal pump. So again, very efficient. You've got none of the head loss associated with pipework, bends and things like that, for example, or pipework being too small. You're pumping the water directly from one side to the other. But as most people know from land drainage pumping stations, they don't actually pump that much. Quite a lot of the stations sluice through gravity sluices the majority of the time. But of course, if you're sluicing through gravity, there is potential energy stored in that water. So can we harness that? And that's really when we're looking at these horizontal type pumps, that's a direction we might be able to look at going in the future. And we're starting to explore potential opportunities to do so. It's not only good from energy perspective, but also very sleek pumping stations, very low construction, aesthetically less of an eyesore to the communities. You've got to remember a lot of the land drainage pumping stations are built in very flat areas of the country because it's protecting a lot of the arable land. So this example here, for example, is one where you could potentially look at using that gravity flow. So take this example here. In this scenario, it's pumping. The water level on the intake is lower than the outfall. However, when the water level in the outfall drops and you can sluice the water through the pump, you could be winning energy back. And of course, if you take enough energy back, it gives the potential of a carbon neutral pumping station. So yeah, as a quick recap, the product capital costs, yes, they're a bit higher. Your pumps are a bit slower and they're bigger because they're slower, which means that the product capital cost is a bit higher. The operational cost, however, tends to be lower. Because they're slower, your bearings are rotating less, your seals are rotating or moving against each other less. Everything needs less maintenance. Your asset life is also generally increased, again, because it's moving less. And you can see this with the amount of pumps that are still in operation that are over 70 years old, some of them. And therefore, we believe that with the fish-friendly pumps, when you look at it from a total life cost or a total expenditure over the life of the asset, it is better and more cost effective than the pumps that we've seen throughout the 90s and the early 2000s before fish friendliness was a thing. Well, before fish friendliness was a requirement. Thank you for listening. I hope that was of interest, and I think I've managed to keep it in just in time.
You have, Martin. Unfortunately, we don't have any time for any questions now. But if anybody does have any questions, as you can see, we've got Martin's details on the screen now. So if you want to make a note of those, I'm sure Martin will be quite happy to receive those questions and answer them if he can. So if I could just say thank you very much to Martin for the presentation. It's been very enjoyable, very interesting, and the next two sessions will be shown on the next screen, and hopefully you'll be able to join us there. So thanks, Martin. Thanks, everyone. And goodbye for now.
Thanks, Kevin. Thanks, everyone.